Okay, this is going to be material for test 1D. It's on motion graphs. Okay, so we visualize motion with different kinds of graphs. First graph we're going to talk about is a position versus time graph. Really, I should say it's x versus t, but then because x means position, but that looks confusing because position will always be on the y-axis. Okay, so like I just said, the y-axis will have position, and the x-axis in all my motion graphs will be time. So here we have a position versus time graph. These points are data points where the position was measured for at different time intervals. Looks like every second the position was measured for this object. Okay, and then a line of best fit was drawn through those points. Okay, so what's significant about this graph? Well, there's one important thing you're supposed to be able to do with any motion graph. That's to interpret the slope of that line of best fit. Okay, just recall, slope is rise over run. For any graph is the rise over run. The changing y over the changing the x values. Okay, so all you do is pick 2 points on the graph. I know you've had this before. And pick 2 points. Let's say I pick these 2 points. Okay, so the rise would be how high. You write a little right angle triangle between those 2 points. Then you just go, what is the rise? For that triangle I picked is 20. And then the run is 4. So rise over run is 5 meters per second. Okay, it doesn't really matter how you draw the triangle. I mean, where you draw the triangle, it doesn't matter. I could have done this triangle like I showed here. There's pick 2 other points. It would be the rise would be between 5 and 15, which would be 10, and the run would be between 1 and 3, which would be 2, and it still comes out to 5 meters per second. Okay, so I'm sure you've found rise slopes of lines before. Okay, now look at the units. units meters per second. That's the unit for velocity. So the slope of a d versus t graph is the average velocity of the object during that trip. Okay, I highlighted. That's very important. I highlighted that in yellow. Slope of a position versus time graph is velocity. So if you look at this graph right here, this is a graph of these two runners, position versus time graph. Okay, so slope means the velocity, right? So which of these runners is moving faster than the other? The red runner or the blue runner? Okay, slope is the steepness of the line. So the steeper line has the bigger slope, and so therefore has a bigger velocity. So the red runner has the bigger velocity over the blue runner, and I can figure out what those velocities are, and this way I did in those blue boxes there. Okay, so it looks like I picked when I'm finding slopes. Okay, so to find the speed of the red jogger, I pick a corner on the grid box, maybe that one, where the line hits the corner of a grid box. And then maybe this one right here. Looks like it hit the corner of a grid box. So the rise over the run, 4 to 2, would be 2 over 1 to 2, 1. Or you can pick any box you want. And that's why I get 2 meters per second for the red jogger. The blue jogger do the same thing. I mean, doesn't matter what size box you pick this one, because there's a corner there, so that'd be 3 over 3, which is 1. Okay, so basically you can see that without doing the math, you can see that the red jogger's line is steeper than the blue jogger's line, and so the red jogger is moving with a quicker speed. I don't like to do this, the delta x over t, because delta x confuses you with the x component, the x axis. So it really is y over t, changing y over changing x. Now, velocity can be positive or negative, as we said before. If you're moving toward the right, let's not worry about this, heading away from the detector. So velocity can be positive or negative. Positive velocity means moving to the right, or moving up. Usually that's what or moving north or moving east. Negative means moving to the left, or moving down, or moving west or south. Okay, so we know that already. Don't worry about this in lab, because we got different detectors now. We'll see that in lab. So Okay. But you also can have zero slope with a horizontal line. So if you have an uphill slope, it's like you're climbing a hill. The velocity by definition is positive. If you have a downhill slope on a d versus t graph, you're going to have negative velocity. And if you have a horizontal line, zero slope, you should know that. There's no rise, there's just a run. That would mean zero velocity. So, in all these graphs, we have the velocity staying constant because the slope is not changing. If the slope is not changing, the velocity is constant. Okay, so in graphs, in the positive velocity and negative velocity graphs I showed you, you have speed and it's staying constant. It's not increasing, it's not decreasing, it's staying the same because right here the slope is the same as right there. Anywhere along that line, the slope remains the same anywhere along those lines. Now here, you would not call that uniform motion because it's at rest. So if you have a horizontal line, you wouldn't say it's inconstant. It's the velocity staying constant because there is no velocity. Okay, so I like this problem. To ask questions about it, yes. So let me ask you a few questions on here. Rank these according to increasing speed or velocity. Now, negative velocity doesn't mean it's a negative velocity. Just means it's going downhill. It doesn't mean that it's smaller than a positive velocity. So, for example, if I looked at, let's see, for example, if I asked you who has a bigger speed or velocity, A or D? Well, there's no numbers here, but we can figure it out. D has a slope. I'll just say velocity because velocity is slope. The velocity at D is, for trip D, is 2 over 2. I'll just assume each of those blocks is 1 by 1. Whereas the velocity of A is, I'll just use this one between those 2 points. The velocity of A is 2 over 1. So, but it's negative because it's downhill, so it's negative. Now, you're not going to say 1 is bigger than negative 2 because the negative just designates the direction. So, the velocity of A is greater than the velocity of D. So you do absolute values when you're comparing the magnitudes of this velocities. Okay, so tell me which ones are negative velocity in this graph. Okay, all downhill ones, right? So letter C, letter A, and that's it. You read left to right. How about the positive velocity ones? Well, that's everything else. That's green. B and D. Okay, who is the fastest? Who's the steepest? Well, I mean, it's kind of hard to tell. We already did A, it's negative 2. We did D. B looks like, let's pick a corner. B looks like 3, a rise of 3 over a run of 2. It's 1.5. And the other one is, let's see, what else do we do? Guess we didn't do C. C looks like it's 1 over 1. So VSC is 1 over 1. So it's tied with D. Okay, so if we were to rank these according from largest to smallest velocity, fastest to slowest, don't use the natives. Don't let that. So the fastest to slowest average velocities. You go from the steepest to the less steep ones. Okay, so fastest one would be, let's see, we have 2. So VA. And then we got 1.5 over here with B. And then we got a tie between C and D. Okay, so that's how I show it. When you have a ranking problem, okay, no. Okay, so here's a distance versus time graph again. Where is he moving the quickest? Okay, that would be in this section between 16 and 18 seconds. Okay, so the quickest speed is during time 16 to time 18 seconds. Where's he moving the slowest? Well, you're not going to say 18 to 20 right there because he's not even moving. That's where his zero speed. Okay, so you pick the slope that's the less steep. So right there, the slowest speed would be a time of 20 to 25 seconds. That's where you're slowest. Okay, so I'm just asking you to find the speeds and velocities here. Speed is just the magnitude of velocity. So let's find the velocities. 0 to 3 seconds, you have a horizontal line right here. So that's zero speed, zero velocity. 3 to 11 seconds, Um, you know what? It's kind of hard to see this, but we could go. The bigger the triangle is, the better, more accurate. So I'm gonna pick this corner of a box and this corner box. 7 minus 3 is 4 for the rise, and 10 minus 6 is 4. So the velocity would be 4 over 4, or 1 meter per second, and it's a positive 1. The speed is the same because it's just the absolute value of velocity. Okay, now when I say at the 8-second mark, what's the velocity? You're not going to just do 5 over 8. That's a big mistake that people make. Common mistake people make. So what we're going to do at the 8-second mark, you're not going to do 5 divided by 8. You only can do that if that section starts at 0, 0, which it doesn't. So instantaneous velocity is the same as the velocity of the average velocity of the line that point is. So this point right here at 8 seconds is part of this line between 3 and 10.5 seconds that we've already figured out the velocity for. So I'll just use the 4 over 4 box, so it's 1 meters per second. Again, if they ask for instantaneous velocity, look at the line segment that point is part of, and then find the rise over run of that line segment. Okay, at 14 seconds, well, that's easy. At 14 seconds, you're up. The instantaneous speed at 14 seconds is the slope of the line that point is a part of. And that slope is 0. 17 seconds. Right here. I don't know, somewhere right there. Okay, so you have to find the slope of that line. So the rise is 8 minus 2 is 6. The run is 16 to 18, 2. So the velocity is 6 over 2, but it's negative because it's downhill. And the speed would just be 3 meters per second. You don't put negative when you're talking about speed. Okay, so again, don't do 5 divided by whatever that 16, 5 divided by 17. That's not going to give you the answer. You just don't pick a point and go 5 divided by 17. You just don't do that. Okay, and then 22 seconds, right here, find the slope of this line. I would do, the slope is, the rise is 2, the run is 20 to 25, it looks like. So that's 5 2/5. So that's downhill 2. So that's negative 2/5, which is 4/10, negative 0.4. No, 1/10. Wait. 4/10 is 0.4. And so this would be 0.4 meters per second because there's no, it's the absolute value of velocity. Let me just double check that. Okay, so 2. Okay, let's figure out the average trip speed. So to do that, speed is the total distance over the total time. D net over time net. Net distance over net time. So the total distance traveled. Okay, we gotta figure this out. So from 0 to 3, I did 0 distance. Okay, from 3 seconds to 10 seconds, I did 8 meters. So let me just keep a running tab here. And from 11 minutes to 16 minutes, I did 0 meters because I didn't go anywhere, I was stopped. Then from 16 to 18 for this section, seconds, I went 8 to 3. So I went 5 meters. Then I went 0 meters here. Then I went 2 to 0. I did 2 meters there. Then 0 for this trip. And it looks like I did 29 seconds total. Okay, so 0 plus 8 plus 0 plus 5, 13 plus 0 plus 2 is 15 plus 0. So 15, distance is 15 meters over 29 seconds. And I get 0.52 meters per second. Okay, what's the average trip velocity? Okay, velocity is the net displacement over the total time. So total time is still 29 seconds. The net displacement, okay, here's how you do it. You go from the starting position to the finish position. Whoa. The starting position is 0, and the finishing position is 0, and you subtract those two numbers. So the change in x is xf minus xo, which is really yf minus yo. It's the position, the final position minus the original position. In this case, it's 0 minus 0. So I have the average velocity is 0 meters per second for the whole trip. That's kind of a weird thing. Okay, so this is just kind of a review. We have a position versus time graph. What's the instantaneous speed at 35 seconds? Let's find 35 seconds. That's right here. So right here, what did I say? Instantaneous speed is the speed to measure the instantaneous velocity or instantaneous speed. You find the slope of the line segment that point is part of. So the line segment here is horizontal, so I know that's 0. It's not moving. How about 40 seconds? Right here. Okay, so you take the rise over the run. The rise looks like 12. Minus, looks like 3. Okay, so really it's 3 minus 12 because it's the final minus the original. So, but I just do 12 minus 3 and then make it negative. So that's 9, but it's negative 9. Because it's going downhill. Okay, and then the run looks like, well, this is kind of tricky. The run, what would that be? That looks like 38. There's 30, there's 35. There's 40. It's between 35 and 40. So that's 38. I have no idea what this is. It looks like it's 47. So 47 minus, what did I say? 38. No, you know, there's kind of error there. 47 minus 38 is 9. Okay, so the rise or the run looks like it's negative 9 over 9. So it's like negative 1 meters per second. What's the average trip speed by the 50-second mark? Okay, so by here, trip speed. Okay, so I went 6. Oh, speed is distance over time, net distance over time. So I went 6 plus 0 plus 6, and then 0 plus 12 to 3 is 12 to 3 is 9 plus 0 oh wait, so I'm only going to 50 seconds, so that would be right here. So it's still plus 0 over the total time of 50. I get 0.42 meters per second. Okay, so next thing they're asking is average trip velocity. So that'd be the displacement over the total time. So over 55 seconds, what's the displacement? When you get to 55, that would be right here. Okay, so all you do, displacement is final position minus original position. The original position is 0. And the final position is 6. So my average velocity for 55-second trip, 6 divided by 55 which is 0.11 meters per second. Okay, sometimes I'm going to give you a scenario, and you're supposed to pick the right motion graph for that. So, let's look at this. A squirrel descends an 8-meter trip kind of speed. Okay, so descending means going down. That's negative velocity. And it'll be a straight line because you're going constant speed, a straight downward slope line. So, where do we have a straight downward slope line at the beginning? So we don't here. We have uphill. We don't here, so exclude those. It remains still. So for a little bit, there'll be a flat line because you're at rest. So the second section has to be a flat line. Well, in both those cases that remain, I have a flat line right here and right there, so I can't pick those yet. Okay. Then runs back up the tree in point 1 to his exact starting position. Okay, so both of these he has the upward velocity. That means a positive velocity because he's going up. So we got positive velocity. It doesn't say he's going at constant speed, but both of these have constant speed. Looks like. But which one ends at the same position that he starts? Oh, this one. This one, he didn't go as high at his position that he ended is lower than the position he started from. So this would be my right answer. Okay, here we have 6 different position versus time graphs, or D versus T graphs. Okay, so you should be able to do this. So maybe make a little chart, the V, for the different graphs. Okay, so graph A, B, C, D, E, F. Okay. Graph A is a horizontal line, so it has 0 speed. Graph B is a horizontal line, it has 0 velocity. Graph C is uphill, so it has positive velocity. That doesn't mean the speed's increasing. You can see the speed. You have a constant slope the whole time, so speed is not increasing. Just positive velocity going uphill. Letter D, same thing. Letter E, negative velocity because it's downhill. Letter F looks like positive for the first half and then negative for the second half because the second half goes downhill. Explain what is happening to the traveler in the last graph. Well, I kind of said that he changes his direction right there. We assume this is a straight road, no curving. Make this all easy. All these graphs I give you in this section, we assume that it's a straight road. So the guy's moving to the right, then he comes to a sudden stop because he has to turn around, and now he's moving back in reverse. Which 2 graphs have the same speed but different velocities? Okay, if you have the same speed, you got this. You got the same slope. Absolute value is slope, but one's positive, one's negative. So it looks like it's that case F. So you got, I could figure out that slope is 8 over 5. This slope is about 8 over 5, but negative. Let's have 0 for the whole trip. Well, that's easy. We already did that. A and B. Which graphs have 0 for the whole trip? Okay, which graph has 0 the entire trip? I don't know why I'm asking that again. Okay, I mean, basically, either one of these questions is the same. Which graph but the traveler only stopped for a moment? Okay, that would be letter F, because you had positive velocity and then you had to turn around for if you're going forward and then you reverse, you gotta stop for a moment. So that'd be letter F. Okay, so looking at this, each grid box is 5 centimeters tall, so I should have made this. I should have made this centimeters right here. The position in centimeters. Okay, so then 0.1 seconds. Okay, average speed of the entire trip. Okay, average speed is distance over time. The total time looks like it's 0.8 seconds. The distance you traveled is 25 here, section 1. Then all the way down to here is another 25, right? Then right here was 1, 2.5. 2.5 times 5 looks like 15. This is negative 10, negative 5, negative 10, negative 15. So that looks like it's negative 13. So I got 13 there. Then right here is another 13. So let's add all those numbers up. 25 plus 25, 50 plus 26 is 76. I get 95 centimeters per second. What's the average velocity of the entire trip? Well, again, oops. This is supposed to be average speed right here. S with a bar on it. Average velocity is the displacement over time. The total displacement looks like the starting position and the finishing position is 0 again. So that'd be 0 centimeters per second. Okay, so we've been talking about things. If we had speed, we were going constant speed, except where the speed changes very briefly. So in the graphs that we've been talking about, D versus T graph, If you had a line like that, then a line like that, this is constant slope, so that's a constant v, and this would be a slower constant v because it's less steep. But right here, to go from a faster to a slower, you had accelerating at that small little turn, because you're going from a faster speed to a slower speed, so your speed's changing. But if I magnified that, it would look like a curve. So it looked like a little curve. So whenever you have a curved part on your diversity graph, you have acceleration. Okay, so let's talk about those little curvy things. So I zoomed in on that little bend. Okay, we already talked about acceleration. Uniform acceleration means the speed's increasing at a constant rate. Every second is picking up the same amount of meters per second, or every second is losing the same amount of meters per second. For example, a falling object, freely falling, when it's descending, picks up 10 meters per second. Every second it falls. That's uniform acceleration. Okay. What shape does the line on a diversity graph form when you have constant acceleration? Well, it's a parabola, or half a parabola. So right here, what's happening to the slope of this line? Like right here, compared to right here, compared to right here, compared to right here. The slope of the line is getting steeper. The line does not have a constant slope. The slope is increasing. That means slope on a diversity graph is the speed is increasing. Because slope and speed are the same thing on a diversity graph. Okay, how about here? What's happening to the steepness of this diversity graph? Okay, right here is steep, right here is getting less and less steep until it looks like it's just going to rest. So we get the slope decreasing. That means the speed is decreasing. Okay, since velocity and acceleration, we already talked about this. If the velocity and the acceleration are in the same direction, the speed is increasing. If the velocity and acceleration are in opposite direction, the speed is decreasing. So here's the 4 scenarios we've already talked about. So let's look at this. What kind of velocity is this? Uphill. So we got positive velocity because it's going uphill, and the speed is decreasing. No. Positive velocity, and the speed is increasing because the slope is going up. The slope is being the velocity or speed. And so, therefore, if this would be positive acceleration, according to that table that we just memorized before. Okay, in this case, we have positive velocity because it's still uphill. The speed or the slope is decreasing. And so this would be, since the speed's decreasing, the velocity and the acceleration have to have opposite signs. Okay? Okay, so this is just reminding you that the car going forward, positive acceleration, speed's increasing. Don't worry about these motion diagrams right here. I don't really go through that. But in these two cases, this case, the speed is increasing. This case, the speed is decreasing. Those are the two cases we just talked about. These two cases, if you have negative velocity and negative acceleration, because the signs are the same, this speed will be increasing. And negative velocity, because you're going to the left, positive acceleration would mean the speed opposites fight each other. Speed decreases. Okay, so I should show you what the pictures look for these. Each one, let's just do this again. The graph for this one would look like the D versus T graph. Would look like this. Positive velocity increasing. Okay, for this other one, positive velocity decreasing. How about this one? Negative velocity. Okay, so I have to downhill, and the speed's increasing. So it had to look like that. The slope's getting steeper and steeper with time. Okay, that. And then what if I had negative velocity decreasing? It would look like downhill. The slope would be flattening out. Okay, so you should recognize these graphs for these different cases. Which graph represents the motion of an object moving with positive velocity and negative acceleration? Positive velocity means uphill. Negative acceleration means, okay, if you have positive velocity, negative acceleration means opposite is slowing down. So that means the slope gets flatter, less steep. So we got positive velocity has to be going uphill. And it has to be getting slower, so the slope has to be getting flatter. This is the answer. Okay, you can see it's getting flatter, and it's going uphill. Okay, this one. Okay, so here we're going to practice this. What's velocity in each one of these? These are all D versus T graphs. So downhill means negative. Downhill for the first one, downhill for the second one, downhill for the third one, uphill for letter D and E. Speed increasing, decreasing. Okay, what's the slope doing? The slope is getting steeper in part A. It's getting steeper in part A. So the speed is increasing. In D, the slope is not changing. The slope is the same as we go down this line. The slope is the same, rise over run. So constant, neither increasing or decreasing. In D, the slope's getting flatter, so it's decreasing. I'm sorry, in letter C. Letter D, slope's flattening, so it's decreasing, speed's decreasing. Letter E, we can see that the slope remains constant. Okay, acceleration. Okay, acceleration. If it's increasing, these signs have to be the same. Constant, there is no acceleration. If you have a constant speed, you have no acceleration. Okay, right here, decreasing, so this has to be the opposite sign. Decreasing, so this has to be the opposite sign of the velocity. Okay, the second type of graph, motion graph, that we're going to talk about that you need to learn are velocity versus time graphs. So you have velocity on the y-axis, and again you have time on the x-axis. Now, you got to keep what these graphs mean, separate from what the displacement versus time graphs mean. So that's going to take a little bit of time. Okay, so let's look at this. First graph. When is the velocity increasing? Okay, so it's increasing wherever it goes away from the x-axis. So whenever it moves, whenever the graph line moves away from the x-axis, so if it moves like that, or if it moves like that, so where's it doing that? Well, I don't know how to show it. Right there and right there. Okay, so I say these are second. Okay, that was 1, 2, 3, 4, etc. 5. I say from 0 to 1 second, and from 4 to 5 seconds. Now, a lot of people get this mixed up. They think on a d versus t graph, if you have a straight line, that means constant velocity. And that's not so on a v versus t graph. Okay, so let's do the next one. Where is the velocity decreasing? Okay, so it decreases, the speed decreases when it moves toward, when the graph line, not the object moving, when the graph line moves toward the x-axis. So we can see that right here. That's about it. So it moves towards. And so that would be happening from the 3rd to 4th second. Then finally, where is it moving with a constant velocity? Okay, that's where the velocity is not changing. So right there, it would be moving with constant velocity between, so horizontal line. Indicates that you're going constant velocity, or at rest. rest would be if you were right on the x-axis. Okay, which I don't have on this graph. Okay, so what's the average? This next picture. What's the average velocity here in this next graph? Well, average velocity is VO plus VF divided by 2. So basically, it's staying constant there. So average velocity is simply positive 1 meters per second, because positive velocity is above the x-axis. Determine the average velocity of B. Okay, so for the whole trip, so I go from here to there. So the average velocity equals VO plus VF divided by 2. So VO is 0. And VF is negative 4. So I'm going to divide that by 2. You get negative 2 meters per second. Pretty easy. Okay, so let's look at letter C here. Where's instantaneous acceleration at the 6-second mark? Okay, so I can't just go y over x, 8 over 6. It's not 8 over 6, right? You gotta find the slope of that line segment that that point's part of. So let's see, 12 minus 4 is 8 on the for the rise, and the run is 4. 8 minus 4 is 4. So acceleration is 8 divided by 4. The rise over the run is 2 meters per second squared. That's instantaneous acceleration anywhere on that second line segment. Okay. We're supposed to find the acceleration during these intervals of time. So from 0 to 1 second, to find the slope, 40 divided by 1. That'd be 40 meters per second squared, positive 1 to 4 seconds. So I'll just do a rise over run. The rise is 100 minus 40 is 60. And the run is 1 to 4. 1 to 4 is 3. So that comes out to be 20 meters per second squared. Okay, at the 4 to 12 second mark. Okay, so I see that's a straight line. So really, all I really need to do is find 4 to 12 seconds. Okay. Okay, I don't need to do this whole thing. I can just do a part of it, like this much of it. So the rise is 100, and the run is 9 minus 4 is 5. So this be 100 divided by 5. But you gotta put the negative in because it's going downhill. At what time interval is the object stopped? Well, to be stopped, you had to have a horizontal line on the x-axis. I don't really see that. But whenever you hit the x-axis, you had to stop. Okay, so right there is, let's figure this out. He had positive velocity over here. Then he has negative velocity. So what happened is the object changed directions and had to stop for a moment. So at the 9-second mark, at 9 seconds is where he stopped, but he didn't hang out on that line very long. Okay, so what time does object reverse directions? Okay, well, it's the same graph. So it's where you go from plus to minus. When you cross the x-axis, go from positive velocity to negative velocity or vice versa. When you cross the x-axis, that's when you change direction. So right here, this will be versus t graph. You would say right there, because you had positive velocity here, and then negative velocity going downhill. But we're not talking about that kind of graph. We're talking about v versus t graph. So at what time interval? Well, it's at the 9-second mark. Throwing a blank. It's the velocity positive, negative. Okay, so now I'm asking you about the sign of velocity, and again, anything above the x-axis is positive, anything below the x-axis is negative. So this is above the x-axis right here. 1 to 4, still above the x-axis. And then there's where people mix up. 4 to 9. It's still above the x-axis. It's just that you're slowing down. You haven't changed your direction yet. And then 9 to 14, that's below the x-axis. So that negative. Okay, so speed increasing. Again, speed increases if, on a v versus t graph, if you go away from the x-axis. Like I said before, it decreases if you're going towards it. If the graph is going towards the x-axis. If it stays horizontal, then it stays constant. Okay, so the graph in interval 0 to 1 is going away from the x-axis. So it's increasing. 1 to 4, still going away from the x-axis, so it's increasing. 4 to 19. Wait, 4 to 9. 4 to 9 is going towards the x-axis, so it's decreasing. 9 to 14 is going away from the x-axis, so it's increasing again. Okay, so these are your rules. Is acceleration plus or minus? But I don't even need to use the rules because I can see if it's uphill, it's positive on a v versus t graph, and if it's downhill, it's negative. So 0 to 1, positive acceleration, uphill, next session, uphill, next session, downhill, and then last section, still downhill. Now just check from what you know. If you have two pluses, acceleration, velocity, you know the speed's increasing. If you have plus, okay. If you have plus and a minus, you know the speed's decreasing. If you have two minuses, you know the speed will be increasing. So it jives with what you were taught or learned earlier. So two ways, as you could have, well, if the object is moving with constant or the object okay, so on a v versus t graph, if you're asked about the distance or displacement, it's kind of weird. This would be the area between the graph line and the x-axis. So we can look at this and which travels the greatest distance. Well, if you just look at A, the area between line A and the x-axis is the biggest. If you did two other ones, you could see that A is the biggest. So if I did D would be, but then it has this distance as well. But still, you put those two triangles together, it's not going to be the light gray color at all. And then I guess B would be that much, pretty much. And then C would be the smallest, probably. Okay, so which travels the greatest distance? That would be the area under the graph A. Graph line A is the biggest. So, which travels the shortest distance? I would say the area under C is the smallest. D looks bigger. Now you have actual numbers, so I'll say C, but I'm not really sure. Which changes directions during the run? Okay, he had positive velocity and negative velocity. So that would be letter D. he who crosses the x-axis. Only line that does that is D, which starts to run from a rest position. Well, that would be any line that starts from 0 on the velocity y-axis. Looks like only one, and that's B, which ends the run at rest position. So he ends up at the same place that he started. Okay, so that means the displacement, delta x, the displacement is 0. So now, when I say the distance area under the graph line, between the graph line and x-axis, if I'm saying displacement instead of distance, it's the same thing, except areas below the graph line, the x-axis, areas below the x-axis are negative displacements. Areas above are positive displacements. So really it doesn't matter if it's above or below. If you're talking about the total distance traveled, it only matters if you're talking about displacement. So this guy started with a negative displacement and he ended with a positive displacement, but both those areas cancel out each other. The one on the right is positive, the one in dark gray is negative. They're equal areas, so they cancel each other out. So that'd be choice D, which slows down at a constant rate the entire time. Well, that means who's moving closer to the x-axis for the whole trip. And there's only one guy, C. D moves closer for half the trip, then he moves further. Which speeds up at a constant rate during the entire. So speeds up means moving away, constantly moving away. That'd be letter B. So which runner slows down and then speeds up? So he's going closer to the x-axis and he's going further from the x-axis, the graph line. And that would be choice D. So those are conceptual questions. Checking if you understand concepts. Okay, so here's an easy one. V versus T. Velocity is a function of time. That's all that means. What is acceleration? Okay, this is elementary. Pick any right triangle that has 2 points at the corners of grid boxes. So 5 minus 3, the rise is 2, 5 minus 3. Then the run is 5 to 15, which is 10. So this would be 2/10. It would be positive. It'd be positive because the slope is uphill slope. find acceleration. Again, you can do anything. You can make any box you want. I can make this triangle I meant. So this is 25 over 10. 25 over 10. But it's going negative. So, because it's downhill. Okay, if you need to find the instantaneous acceleration, you're going to have to draw a tangent. And we can do this with our lab equipment, but I'm not going to have you do this on an actual test because, you know, it's hard to draw a tangent. So this is showing what is the, at this point, which looks like 30 seconds, what is instantaneous acceleration? Okay, so I try to draw a tangent which touches the graph at one point, and it kind of, I don't know how to call it, looks like a bow tie even on both sides of the knot. So anyway, then you find the rise over the run of that slope of that tangent, and that'll be your acceleration. So that's what they did. 260 minus 210 is 260 minus 210 is 50. And then 50 minus, that's just 50. So it's 50 divided by 50. We get 1 meter per second squared is positive. Is positive because it's going uphill. Okay, we're not going to really have curvy lines on a V versus T graph because finding the slope isn't that easy. Now, if you had calculus, that's integrating. Okay, area of a rectangle is base times height. Base times height. Area of a triangle is base times height divided by 2. So, here's the height. Here's the base. Base times height divided by 2. Okay, so let's find displacement in these graphs. So here's the 0 mark. So this looks like a triangle. Here's the x-axis. The area between the x-axis and the graph line makes a rectangle. So that'd be 4 times 10. The area. 4 times 10 is 40 meters per second squared. Oops. It's meters per second times seconds, which is just meters. Okay, what's the net distance traveled? 40 meters. What's the net displacement? Because it's positive above the x-axis, it's positive 40 meters. Next. How about this one? What's the net distance traveled into the V versus T graph? So that looks like 4. So the base is 10. The height looks like is about 24 minus 4. Then we're going to divide that by 2 because that's the area of a triangle. So 10 times 10 is 100 meters. What's the net displacement? Same thing. What's the net distance traveled for this entire trip? I don't know. That looks like it's 10.3. I'll give you a graph line, a grid, so you won't have to worry about that. Okay, so we're going to have to find the area of that triangle, the area of this rectangle, and add them. So net distance traveled is 12 times 4 divided by 2 plus the area of the triangle, 12 times I'm sorry, it looks like 10.5. Okay, 12, 10.5 minus 4. Okay, that's the base. So this would be 24 plus, get my calculator out. So that answer is 102. Since it's all above the x-axis, here's the x-axis right here, it's all positive. Net displacement's the same thing as the positive 102 as the distance. Okay, getting a little trickier here. Okay, what's the net distance traveled? Okay, here's that. This looks like the x-axis right here. And we got negative distances, positions. Oh, wait, this is a d versus t graph. So I don't have to do an area thing. So all I do is, he went from 0 to, I don't know what this is. This looks like 550. Okay, so he traveled from 0, to 550. So negative, distance 550 meters, or net displacement will be negative 550 because he's moving. Okay, on this one, check out where the x-axis is. And I guess I'll estimate that one to be halfway between 1.5, 10.5. So let's make it easy. Let's call it 1.3. This looks like it's 5.5 there. So the area, if I want the net distance traveled, I just find the area of each of these things, triangles in this case. Okay, so area of that one is 5 times 0.5 divided by 2. So 2.5 divided by 2 is 1.25. meters. This area is 1.3 minus 0.5. That's the base. 1.3 minus 0.5 times the height, which is really the depth, times 8 divided by 2. So that comes out to be 1.3 minus 3.2. So the net distance traveled is the sum of all those areas. 1.25 plus 3.2 is 4.45. Now, when you find the net displacement, you gotta make that area that's underneath the x-axis, you're gonna have to make that area negative. So your answer is going to be that area's above minus 3.2. That's going to come out to 1.25 minus 3.2, negative 1.95. Okay, so that's what's left when you add the negative area to the positive area. This is a v versus t graph. I want the net distance traveled during this trip and the net displacement made during this trip. So on a v versus t graph, to find distance or displacement, you got to do the area between the x-axis and the blue line, the graph line. So first I'm going to break these up into triangles and rectangles. This looks like one whole triangle, so I'll keep this one. Okay, so this triangle here, the area equals 60, the height, times the base, times 10 divided by 2. So that'd be 300 meters. This is minutes. That's okay. This area right here is base times height, so that would be 5 times 60. So that'd be 300 as well. And this triangle area is 60, that's the height, times the base, 5. Okay, 1, 2, 3. Each one is 5, so that's 15. So 60 times 15 divided by 2 because it's a triangle. So 30 times 15 equals 450. And this triangle area equals, the height is 40, the base is 1, 2, 3, 5, 25. 5 times 5 is 25. Each grid is 5. 1, 2, 3, 4, 5. Okay, divided by 2. So 20 times 25 is 500 meters. Okay, so net distance would be 300 plus 300 plus 450 plus 500. And that equals 600 plus 1550. 4. Okay, net displacement is equal to all this. But the last one is negative because he's below the x-axis. So that'd be 600. So 1050 minus 500 is 550. So here's just a review. What does the slope of a d versus t graph represent? So this would be position. I'm going to just say d versus t, okay? So that be, you just memorize velocity. You can figure it out this way. Rise over run. So it'd be meters over the unit for distance is meters, the unit for time is seconds. So that tells you that it is velocity. Okay, this is positive velocity. D versus T graph. It's positive velocity because it's uphill slope. But the slope staying the same throughout the whole trip, so it's constant. So the acceleration equals 0. Constant velocity speed. Constant velocity. Okay, now this graph right here is also positive velocity because it's uphill slope, D versus T graph. But the slope keeps getting bigger and bigger, so speed's increasing. And I could then say it's accelerating, but there's positive acceleration because if it's increasing, the signs of V and A have to be the same. Which part of this graph? Okay, this is the D versus T graph. So what part is positive velocity? Anything right here, because it's a uphill slope. The first part is negative velocity because it's a downhill slope. Positive acceleration. Okay, that's kind of trickier. Positive acceleration. Okay, so on the side we just marked, we got positive velocity. And we have increasing speed because the slope's increasing. So okay, so acceleration would have to be positive because if the speed's increasing, these have to be the same sign. So we also have positive acceleration on that side. Now, do we have positive acceleration over on the left side? Let's just check. Okay, so this left side, we have negative velocity, and it's slowing down because the slope is getting flatter. So the speed is decreasing. And so we would have to have positive acceleration there as well. Because the speed's decreasing, these signs had to be opposites. So everything, both sides, entire graph shows positive acceleration. Okay, this part shows positive velocity, the d versus t graph. So anything going uphill, so A through C. Which part shows positive acceleration? Okay, so let's check. The first part has positive velocity. This first part, A through C, positive velocity, but it's slowing down. Speed's decreasing. So this has a negative acceleration. So it can't be that side. How about the right side? C through E. Here we got negative velocity because it's going downhill and it's getting faster. It's getting steeper. So the speed is increasing, and that means the acceleration has the same sign. So no part has positive acceleration. Both sides have negative accelerations on that graph. Okay, let's look at example 5. Okay, which part of the graph represents positive velocity? Okay, positive velocity is whenever you have uphill slope on the d versus t graph. So that only would be there. So between B and C. Next part, which part represents positive acceleration? Okay, acceleration only occurs where there's a bend on a d versus t graph. So it could be right here. It could be right here, or it could be right here. Okay, this one looks like this up close. This one looks like this zoomed in. This one is pretty obvious. I don't have to redraw it. Okay, so how can you have positive acceleration? Positive acceleration will occur when you have positive velocity and the speed is increasing. Or when you have negative velocity and the speed is decreasing. Okay, those are two cases where you'd have positive acceleration. Okay, so let's check this out. Okay, right here we have positive velocity and the speed is increasing. So right there would be an answer. So at B. Let's check the other ones. Okay, change the color. Check that one. So right here, we got positive velocity and speed is decreasing. So that's not it. Then right here, we got native velocity. The speed is increasing. So that's not it. Okay, how about right here? Okay, right there, we got native velocity and the speed. The velocity speed is decreasing because it's flattening out. Okay, so right there also is positive acceleration. So that would be at D through E. Okay, I doubt I'll ask you that particular stuff, but it's good to know. Okay, next example. Is the speed greater during the first 5 seconds or the last 5 seconds? Well, the speed is 0. The slope is the speed. It's 0 at the last 5 seconds, so it has to be the first 5 seconds. The slope is, I can tell you the slope is 25 divided by 5. 5, do this. The speed is the slope, so that'd be 5 meters per second. But it's 0, where it's flat. Constant, negative 2 meters. Okay, I don't know why I wrote constant twice. Okay. You're not going to have to sketch graphs, but you'll have to identify them. Okay, so I want D versus T graph. I'll make this meters. I'll make this seconds. So it doesn't matter where you do it. Let's make it going downhill because it's native. Okay, make the slope negative 2. So I guess the easiest way to do this would be something like this. Downhill 2. So I'll say that's 2. I'll say this is 0. And I'll say this is 1. Okay, so the slope is 2 over 1, native. Kind of stupid. But you'd have to identify it. So my graph would look like this. Now, you can make any scale you want, etc. Okay. How is this origin from velocity versus time graph? The slope. How is this in terms of the area between the graph line and the x-axis? But it's negative if below the x-axis if you're talking about displacement. Motion on the following graph. Okay, this is a v versus t graph. So it looks like it's negative 3 meters per second constant because it's a horizontal line, it's not changing. Describe motion. Okay, this is a V versus T graph. It's positive velocity. Increasing speed. I can say it starts from rest because it started with 0 velocity on the 0 mark. What else? I can say acceleration has, because it's increasing speed, has positive acceleration, or because it's an uphill slope and the slope is V versus T graph. I also could say that acceleration is constant because it's a straight line. Which of the following graphs shows the greatest acceleration for, okay, it's the steepest one for the first 6 seconds. Well, obviously it's not this one because acceleration is slope and slope is 0 if you have a horizontal line. So it's between these two. Now if you look at this, they have the same rise, except and this rise is 4 as well, but this run is 6 and this run goes to 7. So this guy is steeper, and so he has a bigger acceleration because the slope's bigger. 4 over 6 is greater than 4 over 7. Okay, showing acceleration again. I don't really know. This looks like it goes to 5.5. So acceleration looks like, or I could do the whole thing like this. The run is 3, and the rise is 3 minus the negative 3 is 6. So the slope would be 6 over 3. And it's positive because it's going, the rise over run. Because it's positive because it's going uphill. So that's acceleration. Okay, same idea here. This is a V versus T graph. Acceleration is, I could just do one of these because it's so clean. Acceleration equals negative because it's going downhill. The rise is 2, the run is 1, 2, 3 seconds. The rise over the run, 0.67 meters per second squared. Which time frame is the acceleration the greatest? Okay, so, well, it's a V versus T graph, so you get the same acceleration on both sides. I mean, the line is uphill and straight, so both of those, throughout that whole first part, 4 seconds, or the 4 seconds, we can figure out what the acceleration is, but we don't have to. Okay, right here, this is 0 acceleration because there's no slope. So the acceleration is greatest from 0 to 4 seconds. It's the same here as there. From point B to C. Okay, so that would be finding the slope. Acceleration equals the rise 3 over the run. And going uphill, so it's positive acceleration. Okay, draw the corresponding V versus T. Okay, don't give me any. Okay, each big 10 meters tall and 2 seconds wide. Great. Okay, so this looks like two different examples. Okay, so I know this looks like, oops. This looks like the slope of this D versus T graph. Slope is 10 over 2 equals 5 meters per second, and it's staying constant the whole time. Okay, so the slope is 5 meters per second. I go to my V versus T graph over here. And let's see. My 5 is right here, so it's a steady 5 to go past the. Okay, let's look at this one. Okay, the slope, speed here, up to C is 1, 2, 3, 4, 5. 5 times 10 slots. The rise is 50. 1, 2, 3, 4, 5. And the run is 10. 50 divided by 10. But the velocity is negative 5 meters per second because it's downhill. And right here, the slope is 0, so the speed is 0. So I'll have up to C, A, B, C. I'll have negative 5. So here's then it'll jump to 0 velocity. Okay? Okay, so on this one, we got, it's a little different. Okay, so we start out with, okay, we have positive velocity here, first half, and we got slowing down, so we got negative acceleration. And then on this other side, we got positive, we got negative velocity because it's going downhill and it's speeding up. And so we got negative acceleration. So we'll have a downhill slope, straight line, because this is symmetrical. It's the same acceleration. So we'll have a straight line like that. I don't really know what the speed at A is. It's pretty steep. I mean, I could approximate, but I'm not going to do it. It would look something like this. Okay, and with both sides symmetrical. Okay, so we have positive velocity decreasing, negative velocity increasing at the same rate. So this line should be straight. And it should be, I don't know what exactly the speed is. So, okay, let's go. Okay, so they give me a V versus T graph now. I have to come up with a position graph. Okay, so that's kind of easy if you remember that. So the area equals 1, 2, 3, 4, 5, 6, 7, 8, 9. So 90 is the base, and the height is 8. 2, 3, 4, 8 seconds. So 90 times 8 is 720. So 90 times 8. Okay, so it's going to end up 7 native. Now this is a native area, right? So okay, so I don't really know what its speed is. Without, I'm going to have to just add on all this negative value. And so 720, by the time you get to E, 720 would be way down here. And then position, you go from 0 to there. And it's a constant velocity, so this will be a straight line. So it'll be like this. But then there's a break. We'll go all the way down to negative 720. So again, you're not going to have to do this. This is just making you think if you want to. This one, this displacement, this acceleration, this displacement is 1, 2, 3, 4. 4 times 2 is 8. 1, 2, 3, 4. Each of those is 10, so 40. So 40 times 8. And then this looks like it's symmetrical. So this one's 40. So that'd be 2 times 160. This is negative 160. So the position, the net displacement, will be 0. So it would start out at negative 40. And then at point C, it would stop. So, and then turn around to be positive. Okay, so I think I'm doing this right. Okay, so this shows constant, okay, but that's constant acceleration, so it's slowing down. Constant acceleration is slowing down, so I should make this like, oh, to 0. Then it should go like that. Because then it's accelerating at a constant rate, picking up speed. So it looked like something like that. Okay, again, I'm not going to ask you to do that. That's stretching things. Okay, next. Almost done. What's the average for first 3 second average velocity? Okay, this is a position versus time graph, so I just, first 3 seconds, velocity is rise over run. So that'd be 15 divided by 3 equals 5 meters per second. For the entire 10 seconds, I'd have to go like that. Draw a segment from 0 to 10 for the entire trip. That'd be 25 divided by 10. So average velocity would be the rise over run, 2.5 meters per second. Do the same thing here. 1, 2, 3, 4. Draw a line from here to there. Find the rise over the run. So that's 1 over 4. But it's negative because it's downward. Okay, so average velocity is negative 1 over 4, or negative 0.25. What's the average speed? Well, it's the same thing, but the magnitude. Get rid of the negative. Okay, it was the average velocity between 2 and 6 seconds. 2 and 6. Well, it's 0 because there's no rise. Okay, so you draw a line from the start to the finish, and the slope of that line is the velocity. What's the average speed between 2 and 6 seconds? Well, that's 0 too. Okay, right here, this is a D versus T graph. Constant positive acceleration. No, this is constant slope, which would be velocity. So there's no acceleration because you're going constant speed. Okay, that's it. No, it has to do, is equal to its velocity. Yes. No, we don't do area under curves for D versus T graphs. So it's just 2 and 4. Okay, we still have a D versus T graph. Okay, so the slope is velocity. Okay, object 1 has a greater velocity. No, it has a smaller velocity because it's less steep. Okay, so cross that one. Object 2, yes, has greater because it's steeper slope. At time TO, no. If this is a V versus T graph, this would be true, but no, the slope is different at that point. So that's not true for D versus T graph. At time TO, object 2 passes by object 1. Okay, so this is correct because look, at that distance, they meet. The slower object meets up with the faster object, and then the faster object passes the slower one at that time. Okay, so it's 2 and 4. I'll just run straight up with initial velocity. Okay, so this is again D versus T graph. What's the total flying time of the object? Okay, flying, it's not flying, it's like, so the total time is 8 seconds, obviously. What time reaches maximum height? Okay, it looks like it's halfway there, 4 seconds. What is the initial velocity of the object? Heck, I don't know, but I can figure it out. This is on Earth, which I assume it is. So this goes back to another chapter. So the halfway time is 4 seconds. VF at the top is 0. VO is what I'm looking for. A is -10. I'm assuming I'm on Earth. So A equals VF minus VO over T. So -10 equals 0 minus VO over 4. So VO equals 40 meters per second going upwards. Okay, which of represent velocity as a function of objects going upwards. So I'm looking for positive velocity. I'm looking for negative acceleration constant, so a parabola. So this is a V versus T graph. So I'm looking for, and then it slows. Oops. Okay, wait. A D versus T graph would look like that. But a V versus T graph would look like this. Positive velocity stops, and then negative velocity increases until it hits the ground. So it would be this guy right here. Okay, again, this is positive velocity v versus t graph. This is positive velocity decreasing and at a constant negative 10 slope. This would be on the way down. They only showed it like so far. So it's not this one because that would be the D versus T graph. They want a V versus T graph. So it has to be this one. Why isn't this? Okay, so it can't be this one because it starts out with zero velocity and I'm assuming this is a pretty poor question. If this was in his hand, that would be good. But once it leaves his hand, this would be the one. But if this is while being thrown only, letter A is the better one. But I think they're referring to free fall, so I believe it's that one. Okay, let's continue. Which of the following acceleration is function time of an object thrown straight up? Okay, once again, if it has left his hand, it would be negative. Acceleration would be a constant negative 10. So it would be this, A versus T. Would that be negative 10? Now, they're talking about the ball as it is being accelerated in his hand. It would be this one. But once it leaves the hand, it would be this one. Okay. One more. What's the instant speed at 4-second mark? Now, because it starts on 0, you could do 8 divided by 4, but what I would do is just find the slope of the line that it's part of. So it looks like 8 divided by 4, which is 2 meters per second, during which does the object accelerate? Well, anything after 4 seconds, because it's curved. On a D versus T graph, a curvy line means acceleration is occurring. Okay, this is a V versus T graph. What is that? Acceleration time 1. Okay, because it starts on 0, I can just do the slope of 2 over 1. And it's uphill, so it's positive. Time 8. Acceleration time 8 is 0 because the slope of the line is acceleration and there's no slope, it's horizontal. What is acceleration at time? 6 seconds. Well, you take the rise over run of that segment. Okay, make a right angle triangle. Basically, you don't have to do the whole thing. You can just do part of it. So that'd be 4 over 1. Rise over run is 4. But it's negative, it's going downhill. Was a total displacement? I had to find the whole thing. Okay, let's try to do a trick. I don't really see a trick. Okay, this is the area. So I can do kind of a trick here. What I'm gonna have to do is break this up into triangles. These two triangles cancel out each other, so I'm not gonna even count them. Remember, we're doing natives. And then, okay, so the area of this triangle equals 4 times 2 divided by 2. The area of this right here, this box right here, is 5 minus 2 is 3 times 4. That's 12 meters. These cancel out because one's going to be negative, one's going to be positive. The area of this triangle is 2 times 4, but negative. Okay, the area of that triangle is 1 times 4 divided by 2 because of the triangle, so that's negative 2 meters. Negative because it's underneath the x-axis. Okay, so let's add these all up. So it's be 4 plus 12 minus 2 minus 8. So 16 minus 10 is 6, negative 6 meters. So it's really supposed to be negative 6 meters. That's my answer. What is the total travel distance? Well, total travel distance, the net distance is you add them all without including the negative signs. So that'd be 4 plus 12 plus 2 plus 8 is 10. So that comes out to 36. Oops, 16, 26. Four plus 12, 16 plus 2, 18 is 26. Looks like they did that wrong. Oh, I forgot. I had to add these two areas. They don't cancel out because one's not negative, so I had to find that. And basically, that's just like the area of this box because they fit together. So that'd be 4 times 4 times 1. Okay, so I have to add 4 to that. So I'm going to get 30 meters. Ding, 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 ding. Okay, so I had forgotten that these guys don't cancel out. And that's not native. The bottom one is not native, so I just put them together to make a little rectangle. So, what time does the object approach the origin at the constant speed? What? So that would be negative velocity. So 5 and 6 is going back toward the origin, and 9 to 10. Okay, Rex wants to say twice the initial of another. How much higher with the first rep? Okay, well, this stuff is kinematics concept, so I'm going to knock those out. And you know what? We are done with this. Kind of tedious, but simple once you get it. Unit. Okay, sure, you study this.